Hi folks, I think it's time we talked about E. Now I know I've kind of mentioned it in passing it a couple of times, but I really want to get us, or give you rather, a better understanding of what E is. And E is Euler's number, which is this bad boy over here, so 2.7182818284590, so on and so forth. So it's an irrational number, and I don't expect you to memorize this at all. And you actually have a button in your calculator that will tell you what it is. But it's important because it's found just naturally, found in nature, you could say. And a couple of key applications. One is in finance, and the other one is in exponential growth and decay. So we're going to hop into an example dealing with some finance. And we're going to be working with an investment where your interest rate is 100%. Sounds like a lot, and if you find a bank that's going to give you 100% interest on an investment, please let me know. I'd like to do business there. But just for argument's sake, we're going to start with 100%. And you could argue that there are certain situations where you will get 100% growth rates, but we're just going to think about finance for now. So each year, your investment is going to increase by $100. So if you start with $1, after 1 year, you're going to get 100% growth. So that $1 turns into $2. And then in your next year, you need 100% growth. So your $2 becomes $4. And then again, in the next year, you get 100% growth and your $4 becomes $8. And you could keep doing this forever if you wanted to. But hopefully you can see that to get from 1 to 2, we multiply by 2. And then to get from 2 to 4, again, we multiply by 2. And then yet again, each time we're multiplying by 2. Now, in banking, sometimes you will get your interest just added right at the end of the compounding period. But our growth doesn't always happen in discrete increments. Like you're not all of a sudden bang at the $2 mark or all of a sudden at the $4 mark. And an example of this would be your height, or we'll just take the height of a plant, for example. So it's not like you can watch the plant be this tall and then all of a sudden instantly it's a little taller and then instantly it's a little taller again. It's much more incremental, and there's kind of a smaller period of time while it's growing. But it's kind of the same idea. So we'll start with a plant that's 1 centimeter tall. And then to show that we kind of have to have smaller steps in here, I'm going to have some halfway points here. So we still want our 100% growth. But now we're going to have, rather than just the one compounding period, we're going to have two compounding periods per year. So n represents our compounding periods, and in this case, that's going to be 2. So if we're breaking this 100% into 2 separate spaces, then we have 50% with our first compounding period, and then another 50% the second compounding period, adding up to our full 100%. So if we have 50% interest of the height of 1 centimeter here, half of 1 is half, so 1 plus our extra half is 1.5. Now I want another 50% growth on this number, so half of 1.5 is 0.75. So when I add these two numbers together, I get 2.25. So you'll notice that after 1 year again, we have 2 compounding periods as opposed to just the 1. With 1 compounded period, we ended up with 2. Now we're ending up with 2.25. So we're getting a little better investment or a little better growth by breaking our growth rate into multiple segments. And you can keep going with this for a couple more periods if you so desire, but I'm just going to move on in the interest of time. So I broke this up into 2, and I got more out of it. So what happens if I break this up into, say, 10 segments? We'll pretend that these are all even segments, and we still want this 100% interest rate. But now I have 10 segments to break it into, which means I have 10% in here and 10% in there. And in each increment, I'm going to be adding 10% to the previous total. And this is going to be really awesome because I'm going to get more out of my investment at the very end. But it's going to be kind of time consuming because I got to figure out, again, if I start with $1, now I need 10% of $1. So that's 0.1. So 1 plus 0.1 is 1.1. And then I need to get 10% of that. Well, 10% of 1.1 is 0.11. So then it looks like I'm at 1.21. And it's going to take me a long time to figure out what my number is going to be way down at the end of our first year. So there's actually an equation that we can use to solve this. And that is this equation right here. So A equals P times 1 plus R over N to the power NT. So A is the accumulated total, or the total amount at the very end. P stands for the principal, or the initial amount that you're investing. And I should note that this is specifically a finance equation. R is the interest rate that we're expressing as a percent. So 5% translates to 0.05. But in our example that we're using, we had a 100% interest rate. So as a decimal, that would just be a 1. And I briefly introduced you to earlier, that's the number of compounding periods per year. So we break it up into two separate segments. The N would be 2. And then T is our time in years. So let's take a look at this equation with our specific example. Now, we're only ever looking at 1 year. That's all I've looked at so far. We can do more if we want to. And certainly if you're doing investing, you would want to do more than 1 year, but I just want to get the idea of what's going on within the 1 year. So I'm going to let T just be 1 because we're doing it for 1 year. And our principal, we were just starting with that one initial dollar, so we'll plug in a 1 for P. And our interest rate was 100%. Remember, we have to express this as a decimal, so 100% as a decimal is just 1. So I'm going to simplify my equation a little bit by plugging in all of these 1s. So A equals, I'm going to plug in a 1, which is multiplied by something, so I really don't need to write that. So 1 plus, and the interest rate is 1, so I'll plug in a 1 there. Then over N, and we don't really know what N is in this case. And then in our exponent, we have N, and T is a 1. So I'm too lazy to write that 1 down there. So this is a simplified equation for our specific scenario. And the reason I'm doing this is I want to test to see how much I can make by dividing up N into different amounts. So when I plug in these numbers here, we've already done with N as 1 because that was the very first example I gave, where 100% interest and just one compounding period per year. So we ended up with a value of 2 after our first year. So you can plug into these equations if you like, you want to verify these numbers. So when N is 1, that gives us a value of 2. So again, we'd be working with dollars, so these would be dollars. If I plug in an N value of 2, that'll give me 2.25, which is the same thing as I got right here. But we can keep doing this. We can plug in a 4. 4 would give us 2.44140625. And so this would be quarterly, 4 times per year. 12 times per year, well, that's once per month. So if we have monthly compounding, that leaves us with 2.613033529. I'm just going to pause before we get to the next one. Each time, we're getting a little bit more, right? So we got an extra quarter, and then we got almost 20 cents more than before. So each time we're getting a little bit more when we increase the compounding period. So maybe this is approaching something. When we plug in an n value of 52, there are 52 weeks in a year, so this represents monthly compounding. So 2.692596954. And then 365, well, that's daily compounding. So if we have daily compounding, we can plug in 365 for our n's over here. That gets us 2.714567482. But what if you wanted to do like more frequent compounding than daily? You could go like by the hour or the minute or the second, or like a tenth of a second or a microsecond. So basically the idea is we want to have an infinite number of compounding periods per year. So this is continuous compounding. And when you plug in infinity, I know you can't plug in infinity, infinity is not really a number, but as this number gets larger, you're going to get really close to 2.71828182845094, blah, 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 back to the number at the top of our page. And that is equal to E. So this whole expression, we can end up as A equals E. And that's when our n value is approaching infinity. So I called this continuous compounding when we had an infinite number of compounding periods. So this is actually the equation we get if we have a question that calls for continuous compounding. If you come across a finance question that says compounded monthly or something like that, you're going to use our A equals P times 1 plus R over n to the power nt. But if it says the words continuous compounding, then this is probably the equation that you're looking for. Before I jump into a continuous compounding question, I just want to make sure that we can evaluate expressions with e's in them. So to evaluate e, again, I said you don't have to memorize it. It's a number that's in your calculator. So the way you would evaluate this is to use the e to the power x button, or you probably have an e to the power x button in your calculator. So our exponent here, we don't actually see it, but we could write it in as a 1. So you would hit the e to the x button, and then you would hit the 1 button, representing the exponent being 1, and then equals. And that should give you 2.71828, blah, blah, blah. So just take a moment to evaluate these next two in your own calculator, because it's important that you're able to do it on your own. So e to the power 5 is 148.413151. Up next we have 2 times e to the power negative 3. And that gives me 0.099574137. And our last example here doesn't look like it actually has an e in it, but ln of 4 is actually the natural log of 4. So ln could actually be written as log base e of 4. But I'm guessing that most of your calculators, we can't put in the base of the logarithm. So there should be an ln button in your calculator. So to evaluate this, you'd hit the ln button, and then you'd hit the 4 button, and then you'd hit equals. And when you do that, you would get an answer of 1.386294361. So now that we're hopefully a little bit familiar with evaluating expressions with e, let's look at a continuous compounding example. So what is the value of $5,000 after 10 years of being compounded continuously at 8.4%? So here's our equation. A is our accumulated total, and it says what is the value of this at the end. So this is really what we're solving for. P is the principal. So what is the initial investment? Our initial investment is $5,000. E, well, that's just the number E. R is the rate. So our rate is 8.4%. And then T is our years. So that ends up being 10 years. So let's plug in everything that we know. A equals P times E to the RT. A is what we're solving for. P is 5,000. I would put that in brackets. Then we have E to the power 8.4. So 0.084. And then that is multiplying our T, which is 10 years. I should have mentioned that we express this in decimal form, so 0.084 is the number that we actually plug in. And now we're simply plugging this into our calculator. So the number I get is $11,581.83. I had to round to the nearest cent because I don't know anyone who's going to pay me less than a cent. The second item on my list at the very start talks about exponential growth and decay. So E is found in a lot of natural growth in real life. So quite often we're going to use this equation, which is very similar to our previous equation. We had A equals P times E to the RT. So Y just replaces A, Y0 replaces P, E remains the same, K is now represented, or R is now represented as a K, and T is the amount of time stays the same. So very much the same equation, just some different variables you could see. Now, the one key point I want to point out is that our value for K here represents growth if our K value is positive. So that could be something like 12.2 or it could be 0.013. As long as it's positive, then we have exponential growth. If our K value is less than 0, meaning it's negative, then we have exponential decay, which means something is shrinking. So that could be like a population declining over time, or a frequent style of question would be like the half-life of a substance. So we have radioactive material that's getting smaller and smaller. So those would be things like a negative 1.3 or negative 0.5, that sort of thing. So if your K value, your rate is negative, then we are getting smaller. So let's try an example. In 1940, there were 40,000 wild tigers in Asia. In the year 2000, there were 5,000 wild tigers in Asia. Determine the population growth rate of wild tigers over that time. So the first thing we're going to do is we're going to get our exponential growth equation. So we're just going to steal this guy right here and bring him down to our question. So again, Y is the accumulated total, or the final population. So our final population in this case is 5,000 tigers. Y0 or Y0 is the initial population, so that's 40,000. E is just the number E. K is the rate, which we're not sure what that is, but that's what we're looking for, the population growth rate. And then T is the amount of time from 1940 to the year 2000, which I think is 60 years. So let's plug in Y equals Y0 E KT. So 5,000 equals 40,000 e to our unknown value of k times 60. So k is our variable. Remember, e is a number that we know. K is a variable that we really want to solve for. So to get k by itself, let's move this 40,000 to the other side. So you have 5,000 over 40,000, and e to the power k times 60. Now, because my variable or my unknown is in the exponent, I would apply a logarithm. So you could apply any logarithm that you want, but I think it's going to be easier if you apply the natural log, which is log to the base e. So if I say ln of 5,000 over 40,000, and then we have ln of e to the power k times 60. So then, with our log rule, our exponent can be written out in front. So we have ln, and this is 5,000 over 40,000. They're both divisible by 1,000, so I can factor that out. So it gives me 5 over 40. I know I could have simplified farther than that, but I'll just keep it there for now. So we have 60k times ln of e. Anytime you have the base of the logarithm and the argument is the same, that's just equal to 1. So really, I can get rid of this in my next line. I'm going to move over here just to save some space. So ln of 5 over 40 is equal to 60 times the rate. So to get the rate by itself, I just have to divide by 60. So ln of 5 over 40, then I divide 60 to the other side, so this whole thing is divided by 60. That is equal to the rate. So now we plug this into our calculator. And we get negative 0.034657359. You'll probably be given a certain number of decimal places you're supposed to round your answer to, but I didn't state that here, so I'll just list all of them. And you'll notice that the rate is negative because we have a decline in the population. So I know it's called a population growth rate at the top here, but we do have a declining population, so that's why we get a negative answer. Our last example here actually doesn't have anything to do with Euler's number E, but it's just what I thought was a good word problem, an example of something that you could see. So the pH of a substance is defined by the equation pH is equal to negative log of H+, where H+ is the hydrogen ion concentration in moles per liter. So this is going to be a little bit more familiar if you've taken chemistry, and if you haven't, it's okay. It's just a mathematical equation that we can manipulate and solve. If the pH of a substance is 6.62, find its hydrogen ion concentration. One thing that students often struggle with is they struggle to realize that pH is just one variable. Often we use X as a variable, but pH itself is the variable. So there's not two things multiplying, it's just one thing. So let's write out our equation. pH equals negative log times the hydrogen ion concentration of our solution. And plug in what we know. So we know the pH is 6.62. So 6.62 replaces the pH. And then we have our hydrogen ion concentration. Our unknown is our hydrogen ion concentration, so we need to get that by itself. So let's just move the negative to the other side. So we're going to multiply both sides by -1. So negative 6.62 is equal to log of the hydrogen ion concentration. And then we're going to put this into exponential form. So the base of the common log is 10. So we get 10 to the power negative 6.62 is equal to our hydrogen ion concentration. So when we run this calculation in our calculator, we should get the number 2.398832.919 times 10 to the power negative 7. Again, they'll probably give you a certain number of decimal places they want you to go to for this. But I wrote them all out, and it's important that you look all the way to the end of your calculator, because my calculator had all these decimal places, and then it had this E negative 7, and the E negative 7 refers to the 10 to the power negative 7. So important to make sure you're reading your calculator.